We had a problem that looked like this. We were left with this last night, and we were asked to find the acceleration of this system last night for homework. We know what to do with this, right? We have more than one force acting on this. So whenever we see that, we should draw a free body diagram. As you guys were working on this toward the end of class yesterday, and as I was walking around, I noticed a lot of you didn't draw the free body diagram. You have to. You have to draw the free body diagram. Okay, that's the first step. If you have more than one force acting, you need to draw the free body diagram. Now, we said yesterday, I like to straighten this out. Okay, take the 10 kilogram object kind of over here, and the 3 kilogram object over here, and kind of make it on a flat surface, because it makes it easier for me to visualize it that way. I'm not going to insist that you do that, although I think it's a good idea. I am going to insist that you draw the forces acting on this. Okay, I'm going to straighten it out right now. Here's my surface. Here's my 5.0 kilogram object with a coefficient of friction of 0.20. Okay, my 10 kilogram object, if I straighten it out, I've kind of pulled it up like this to the left. That means there's going to be a force acting on object A. That is the force of gravity. It's 10 times 9.81 meters per second squared. Really, it's acting downward, but I'm drawing it horizontally because it's easier for me to visualize that way. There's also a 3 kilogram object that I'm pulling up this way. That's object C. It's going to have a force to the right that's equal to 3 times 9.81, the force of gravity acting on it. Again, really, it's down as well, but I'm going to draw it to the right because it's easier for me to visualize. We have one more force acting here. Yeah, go ahead, Lewis. Okay, so for FA, Lewis is saying for FA, wouldn't it be negative because it's pulling in the opposite direction? On my diagram, I'm going to leave it as positive, although if you want to make one of them negative, you can do that on your diagram. There's nothing wrong with that, but it's not necessary on my diagram. My diagram has the directions labeled with arrows, so that's showing direction. Now, in the end, when I go to plug them into an equation, then it's important to make, an arrow that's drawn to the left a negative value. Okay, I'm not going to worry about that right now, though. Again, if you want to, though, that's okay. You're not going to go wrong with that. Just not necessary yet. Okay, we got friction acting here as well, right? Friction's only acting on the 5 kilogram object. A number of people yesterday were trying to include friction with the total mass, or they were trying to, or just not including friction at all, or whatever. Guys, listen. Friction is a force just like gravity is a force. If gravity pulls on object A to the left, then friction is going to pull on object B to the left or to the right. But it's not going to pull on object A and C because the ground isn't in contact with A and C. So we got a force of friction acting on B. It's going to act to the left. And its value is going to be mu times the normal force. Hey, why is it acting to the left there? Who can answer that question for me? Why is it acting to the left? Yep, Aiden? Good. If the force to the right is less than the force to the left, it's going to move to the right. And if it moves to the right, then friction's got to be, if the force on the left is greater than the force on the right, then it's going to move to the left. And if it's going to move to the left, the force of friction has to be to the right. It has to oppose the motion, right? So friction's going to be to the right. Let's get its value there. It's mu times Fn. It's 0.20 times the normal force, which is 5 times 9.81. And coincidentally, I end up with a force that's equal to 9.81. Don't always make that force equal to 9.81 just because acceleration due to gravity is. It just happens to be this time because 0.2 times 5 is 1. 1 times 9.81 is 9.81. These are my 3 forces. And now I've got to do my next step, which is to say F net is equal to the sum of those forces. FA plus FF plus FB. Doesn't matter what order you add them in. Okay, if you completely reverse them, that's fine. The next step is to say that's all equal to M times A. If we were just looking for the net force, we wouldn't have set that equal to M times A, but we are. Now, what's the mass here? Derek, what are we going to plug in here for the mass? Why 18? Why not 10 or 3 or 13 or 5 or why 18? Yeah, they're all being accelerated, right? They're all relevant to the net force. So let's put them all in for the net force. FA is, now Lewis, negative 98.1, right? We're going to make it negative because it's acting to the left. But now I have to pay attention to the direction. Notice that one was only one of the masses times 9.81. Well, because gravity is only directly acting on that mass, not 18 kilograms. FF is 9.81, positive or negative force of friction. Tony, is friction then positive or negative? Friction's usually negative, isn't it? We're going to make it positive here, though, because it's acting to the, Bart? It's acting to the right. So we're going to make it positive then. FB was, what was FB? 29.43. We're going to make it positive as well. So even though it's gravity, it's really a force of gravity acting on object number C, we're going to make it a positive value because we have it drawn to the right. Now again, the reason we stretched this out like we did is to remind us that these two forces right here oppose each other. One acts to the right, one acts to the left. In my original diagram, it looks like both of those forces are down, and they are. But the temptation is, if I just draw it on the original diagram, we're going to make them both negative because they're both down. We can't do that. If one opposes the other, they've got to be opposite signs. Which one do we make negative, which one do we make positive? Well, that doesn't really matter. But one of them has to be negative and one of them has to be positive. When I redraw the diagram like I did, that becomes a little bit more obvious that one of them has to be negative and one has to be positive. All right, let's solve this here now. The right-hand side is going to be negative 98.1 plus 9.81 plus 29.43. Okay, right-hand side, negative 58.86. Let's divide that by 18. That gives me an acceleration of negative 3.27. Everybody get that? Good. And of course, that's going to be meters per second squared. Yep. Oh, good point. Good point. I never thought of that. Significant figures. How many digits should we have for significant figures here? 2, right? Go back to your original data. This is 2 digits. This is 2 digits. This is 2. They're all 2 digits, right? My least precise piece of data is 2 digits. Final answer shouldn't be 3.27. It should be good. That's right. Yeah. Negative 3.3 meters per second squared. That's my answer. If you did this on a quiz, in a day or two, I would mark it wrong. You do that on a unit test, I would. Now, it's still 3.5 out of 4. If you make a mistake on the significant figures, it's a small thing, but it's something at least. Yeah. Why does significant figures matter? Well, we didn't pay too much attention to it in Unit 1, in our kinematics unit. Not because it didn't matter, but because I didn't want you to, as I was introducing you to real physics for the first time, I didn't want you to get bogged down with something like significant figures, which is a lot less important than the stuff that we actually do from day to day in class. But why is it really important? Okay. If you have, how do I put this? You've heard the expression before, a chain is only as strong as its weakest link. If you have a chain that's 25 links long, and they're all really, really strong, they can all hold a force of 1,000 newtons, except one of them is weak. It can only hold a force of 5 newtons. The most you can apply on that chain now is 5 newtons, because the chain is literally only as strong as its weakest link. Does that make sense? All right. Well, if you're doing calculations, and you know precisely what one of the numbers is. It's 5.214963. And you're able to measure that number really, really good to that many decimal places. And you're able to measure another one, another number, but you're only able to measure it to 3 digits instead of, what is that, 1, 2, 3, 4, 5, 6, 7 digits. That's good. But you're not able to get beyond that decimal place, right? You just, for whatever reason, your measuring device or whatever, isn't good enough to measure beyond 1 decimal place. Well, this chain is only as strong as its weakest link. So if I'm finding the area here and multiplying 5.214963 times 10.0, my chain, my answer is only as strong as my weakest link. Multiply those together, I end up getting 52.1 is my final answer. My least precise piece of data, my weakest link, I can only get to 3 digits. So my final answer doesn't make any sense if I record it to 7 digits, right? It's like saying, that chain that had the really, really weak link is as strong as the strongest link if I count all the significant figures here. If I can't measure to more than 3 digits, it doesn't matter if I have 50 pieces of data, they're all 7 digits, except one of them is 3, that's my weakest one. So my final answer could only be 3. Okay. Does that make sense to everyone? How many people did significant figures in Science 10? Okay. Not as many as I would have thought, actually. How many people have done it in chemistry or somewhere? Science 10, chemistry, something? A few more. Okay. Ask questions, right? Ask those questions, guys. If this is new to you, ask those questions. Okay, we talked about it a little bit as we went through Unit 1. We're talking about it more as we go through Unit 2. Not so much taking a day to talk about significant figures, but just kind of doing it as we go through the problems. Okay. Generally, what I find is that people master it. Okay. People end up being okay with it, but it takes a little bit of time. Okay. Ask those questions until you do master it. Okay. Here's another multi-force problem. This one looks completely different than what we just did. The pulley problems, right? Completely different. Here we got a hill, or an inclined plane, we sometimes call it. Physics people have this way of making things sound complicated sometimes when they really aren't. In physics, we call this an inclined plane. In real life, we call it a hill. Let's keep calling it a hill, because that's a little bit easier, right? We have a 3.5 kilogram block sliding down a hill that's angled at 15 degrees. There is friction of 3.9 newtons on the block. We want to find the acceleration of the block. Well, the first thing that we need to do is draw a free body diagram. We got a picture there, but the picture doesn't really show me anything right now. Let's draw a free body diagram. Let's look at this force of gravity and this force first. What's this force called? Normal force, Fn. Yeah, somebody said it. Now pay really, really, really close attention to what I'm about to show you. If you combine those two forces, Fn and Fg, we get a resultant vector. It's going to be my red vector here. I'm drawing in a different color to make it stand out. That red vector and the normal force will always be at 90 degrees. Always. That red vector is the sum of Fn and Fg, and it shows it down and to the left. I've got it drawn in the position that I want it drawn, but I could also draw it somewhere else. I could draw it up here, or down here, or over here. I can draw it wherever I want. I am going to choose to draw it in one more place, and that's right there. The force that I just drew is not a different force. It's the same force as I drew down here at the bottom. It's the combination of the normal force and the force of gravity. We're going to call it F2 lines, F parallel. That F parallel force is the force that's parallel to the hill. And it is the force that brings something down the hill. When you put a ball on a hill, or you put a box on a hill and let it slide down, Or you put a car on a hill and let it slide down. It rolls or moves or slides down the hill. It doesn't go straight down, right? It doesn't go straight down into the earth. It goes along the surface of the hill. Why? Because there's a force that pulls it down along the surface of the hill. We call it F parallel. But where does it come from? It's the normal force and the force of gravity combined. If I add the normal force and gravity together vectorially, which I can do using some simple trigonometry, and I'll show you that in a minute here, then I get that force, that parallel force. Now, if it's going to slide down the hill, which way is friction going to act? Yeah. It's going to act up the hill or to the right. So let's make this the force of friction up the hill. We know the value of the force of friction already, right? It's 3.9 newtons. We don't know F parallel already. Let's find it. Now, if you're good at math, you're going to follow everything I'm about to show you. If you're not good at math, don't panic about it. Okay? The end result is what we really want out of this. This is 15 degrees. This is 90 degrees. If that's 15 and that's 90, then this one has to be 75 degrees. Right? The sum of the angles inside a triangle are always going to be 180. So that's got to be 75. Does that make sense? Well, this angle right here between the surface and the normal line is going to be 90 because that's the definition of the normal line, 90-degree angle. If that's 90 and that's 75, then this one's going to be 15. The angle drawn at the top of that triangle that we just drew is always going to be the same angle as the angle at the bottom of the hill. Always, every single time. So if you're given the angle of the hill at 15 degrees, then you're also going to be given the angle inside that triangle. Now let's use that to find F parallel. The force of gravity combined with the normal force, the force that pulls it down the hill. Let's say sine 15 degrees is equal to opposite, which is F parallel, over the hypotenuse, which is the force of gravity. So we're going to say sine 15 degrees is equal to F parallel over 3.5 times 9.81. Let's get the value of that. Oops. Let's say sine 15 degrees. Let's press equals after that. Sine 15 it should be. Is equal to 0.2588. Multiply that by 3.5. Multiply that by 9.81. And we get 8.88655. That force is this force. Has this made sense so far? We really have three forces acting on this. There's lines everywhere and arrows and vectors drawn everywhere. But there's really only three forces acting on this box. There's the force of gravity, there's the normal force, and there's the force of friction. The two green lines that we have drawn here are really just combinations of other forces. It's the normal force and gravity combined. We're just simplifying it. I know it looks less simple right now, but in the end, it becomes more simple. Now we're going to say F net is equal to the sum of the forces. It's going to be F parallel plus FF. And F net is equal to m times A. A quick question for you. Why, when I'm doing this, did I not include Fn and Fg? They don't balance each other out. They're not equal and opposite. For the first time, by the way, the normal force is not equal to gravity here, right? Normal force does not balance out gravity. So why am I not including them here if the normal force and the force of gravity don't balance each other out, Stephanie? Right, I am including them. I am including them here. I'm including them with this. Stephanie said I combined them. Yeah, I combined them to get this. So this force right here is the normal force and the force of gravity already combined. Yep. Yep. No, because we said up until now that the normal force would be, we'll just call it m times 9.81, right? But now it's not. In this question, it's not. The reason that it has been the same as the force of gravity is because, look, you got a guy standing on the ground. Gravity acts down. Normal force acts up. Those balance each other out because the guy's not moving up or down. Given a flat surface, normally gravity would be equal to the normal force. And that's been all the problems that we've done so far. But now we're not on a flat surface. Gravity is still m times 9.81, right? It's F parallel over the force of gravity. So the force of gravity is m times 9.81, but the normal force isn't m times 9.81 now. Okay? Carrie, is that what you're going to say for F parallel there? They gave it to me though in the question, right? Good. All right, mass is 3.5 kilograms. The acceleration is, that's what we're looking for here. F parallel, we're going to make it negative 8.88655 because it's down the hill. And the force of friction, we're going to make positive because it's up the hill. It opposes the force F parallel. So we're going to say negative 8.88655 plus 3.9 divided by 3.5. And we get negative 1.42. That's it. So what's different about this problem versus the pulley problems that you did? What's different about this problem versus those more straightforward multi-force problems that we did the first day or so of this stuff? Well, this is exactly the same, right? That's no different. F net is equal to the sum of the forces. F net is also equal to m times A. This part of it is no different. The only part of it that's different is this stuff right here. The force that pulls it down the hill that we're calling F parallel is not a fundamental force. It doesn't occur on its own. It's a result of other forces, the combination of other forces. The normal force that pushes it up and to the left, and gravity that pulls it down. So think about that. You want something to go down the hill, you need a force that's to the left, and you need a force that's down. We have a force that's down that we call gravity. We have a force that's partially to the left that we call the normal force. That combined with gravity gives me F parallel, the force that pulls it down the hill. So what am I including down here? F parallel. Why not Fg and Fn? Because as Stephanie said, we've already included that. That's what F parallel is. Fg and Fn. All right? Carry question. There's your hand there. No. Yep. Good question. If you're finding F parallel, it will be signed, yes. And understand why it's signed, because we're looking for the opposite side, right? The angle is given to me up here, okay, 15 degrees. We're looking for the opposite side. We have the hypotenuse Fg. Now, there may be the odd question down the road, not yet, but down the road where you need to find the normal force. It's not m times g anymore. It is in all those problems where we're on that flat horizontal surface, but now on this angled surface, this hill, Fn is not the same as the force of gravity. How would we find that? Well, we'd say cosine 15 degrees is equal to adjacent over hypotenuse. And that would give us the value of Fn. So it's always going to be sine if you're trying to find F parallel. But if you're trying to find something else, all bets are off. Could be something else. Okay? Yep. Could you use tan 15 and still get the same answer? You mean, yes, yeah. But, I mean, think about what you're asking it. The answer is absolutely, unequivocally yes. But Lewis is saying, if you have the normal force, if you found the normal force, could you use tan in order to find F parallel? Yes, you could, right? Tan is equal to, tan 15 degrees is equal to opposite F parallel over adjacent Fn. But that would be twice as much work, right? Because you've just done the work to find Fn, and now you're doing the work to find F parallel. Here, all we did is found F parallel. We didn't need to find Fn first. So one calculation here would two calculations the way that you're suggesting. Just as right, just as correct. It would still be a 4 to 4 if you did it correctly. But it's a little bit more work, that's all. Okay, yeah, no, if normal force was given, then yes, you could use tan. Yeah. I still don't think it would be any more beneficial than what we have right here, because it's still one trig calculation, but it wouldn't be any less efficient either. Okay? You're going to do a couple problems on these. What you always should do, but especially in these problems where it's a little bit tricky, especially with these ones down here, right? Especially with these vectors right there. Have the example beside you. Literally, have it beside you as you're working on these problems. Okay, if you're working on the problems on the right-hand side of a page of your notes, then have that paper with this example on the left-hand side, or somewhere where you can physically see it as you're going through the next couple questions. One word of caution before we start those questions. Notice, guys, how important it is to have F parallel drawn parallel. Here's what a lot of people will do. And this is wrong. And this is what's going to cause you to get the wrong trig function. Okay, here's my hill. Here's my force of gravity. They do this. Here's my normal force. Is that right so far? So far, so good. Not bad. That's wrong. That F parallel is not drawn parallel to the hill. F parallel is called F parallel because it's parallel to the hill. So you got to draw it like this. And if you found you've drawn Fn a little bit too long to make it parallel to the hill, to make the F parallel to the hill, then just shorten it up a little bit. Okay. F parallel and Fn always have to be 90 degrees. And F parallel always has to be parallel to the hill. That's why we call it F parallel. All right, try those two questions, please, on page 179. We're going to take a peek at question number 2 here now. It says a 55 kilogram skier is accelerating down a 35-degree slope. So here's the slope, here's the skier. Look at that. Look at the quality of this artwork. You don't get that just in any class, right? Go to social class. I bet the artwork isn't nearly this good in social class, right? Allie is smiling and thinking to herself, what are you talking about? That's terrible. But she's smart enough to not say it out loud, right, Allie? Oh, there you go. Good answer. Good political answer. Our angle here is 35 degrees. Now we got to draw a free body diagram here, right? We got to draw the force of gravity acting down, the normal force acting at 90 degrees, and F parallel acting parallel to the hill, 90 degrees to the normal force. I'm going to draw F parallel. Again, there's not two of them. There's only one of them. But I'm just drawing it in two places, that's all. There will be a force of friction that resists the skier's motion, but the force of friction will be up the hill. It'll oppose the motion. Of course, the skier is skiing down the hill. Force of friction is going to be up the hill. Let's get F parallel. We know this angle's got to be 35 degrees because it's always going to be the same as the angle of the hill. Let's say sine 35 degrees is equal to opposite over adjacent. Sorry, opposite over hypotenuse. And the hypotenuse is the force of gravity right here, which is 55 times 9.81. Make sure you're in degree mode. If you're not sure how to know if you're in degree mode or not, then go into your calculator, turn it on, click mode, and it should say degree mode right there. If it doesn't, then switch it to degree mode. Let's say sine 35, let's press equals. Let's multiply that by 55 and by 9.81. You get 309.4731. So F parallel, 309.4732 newtons. That is the force of gravity and normal force combined. Now, as I was walking around, you guys were working on these problems, I had a couple people ask me, well, how am I supposed to find the force of friction? Usually I'm given the acceleration, or sorry, I'm solving for the acceleration, right? Well, listen, just like we said yesterday a bunch of times, don't get bogged down on little things that you might have to do later on. You do what you know. We know at this point we should draw a free body diagram. You might not know if you're going to get the answer yet. You might not know if you're going to run into trouble. But you know that F net is equal to F parallel plus FF. Seth, why am I not including Fn and Fg again? Sorry? We already used them, right? We already used them. We are including Fn and Fg, right? This is Fn and Fg. We already used them to find F parallel, so we're already using them. Good. F net is equal to m times a. It's equal to F parallel plus the force of friction. M is 55. A, we're given this time, it's 4.41, but we're going to make it negative because this skier is skiing down the hill, right? F parallel is negative 309.4732, and FF is what we're looking for here. Would you expect FF to be a positive value or a negative value in this question? Leo, should FF, force of friction, be positive or negative when we solve for this? Why? Perfect answer. Okay, don't second guess yourself. Don't question yourself. You're right. It's a perfect answer. It's going to be positive because it's going up the hill. All right, let's figure out what this is now. Let's say 55 times negative 4.4, negative 242. Let's add the 309 to it. Take the 309 to the left side by adding because it's subtracted on the right side. That gives me FF is positive 67.5 newtons. Oh, wait a second. Anybody else get 67.5? Anybody else get 66.9? What did I do wrong? Oh, did I? Oh, I see, 4.41, yeah, okay. So we're going to go about doing the math the same way, but it's going to work out to be a slightly different answer as a result of that. Good? Crazy hard? Nah, a little bit trickier than the last ones? Yeah, I think so, because we're doing trigonometry now, right? As soon as you introduce trigonometry, people get bothered by that for whatever reason. There's a moving mass of 7 grams is at rest this time, so it's not moving on an incline of 25 degrees on a 25-degree hill. Calculate the force of static friction acting on the loonie. Not sure what to do? Not sure how to find the force of static friction? Do what you know. Okay, first, draw a free body diagram. Okay, nobody should Nobody should be at a loss as to what to do first. Draw the free body diagram. We have a force of gravity acting down. We have a normal force acting at 90 degrees. And we have a force of the hill, or sorry, a force parallel that is the normal force of gravity parallel to the hill, and it's perpendicular to the normal force. Draw that force parallel over here. All right, good. All that to get me one force, F parallel. The other force acting here is going to be the force of friction. Static friction is going to oppose that, right? So we're going to say FSF is this way. Now, we're not looking for FSF max. We're not looking to multiply mu times the normal force. We don't even have mu, and we don't know what the normal force is, at least not right now. We're looking to find the exact value that static friction is at this moment, not the maximum possible value. So what are we going to do? Well, we're going to say F net is equal to the sum of the forces. That's what we do, right? We all know what to do next. F net is the sum of the forces. Again, you don't have to know how you're going to solve this problem yet when it gets to the end. You just have to know what to do next. And we all should know this by now. M times A is equal to the sum of the forces. Okay, here's where you got to think a little bit. The mass of the loonie is 0.007 kilograms. Okay, that's not too bad. What's the acceleration? Okay, what's the acceleration of the loonie? 0. Why'd you say that? Right, it's at rest. There's where you had to think a little bit. That's the first problem we've done with the acceleration is 0. It's always been negative or positive something, but that's okay. It's no big deal. You just got to be thinking just a little bit and recognize that if it's not moving, there can't be an acceleration. F parallel, we should probably have found out what F parallel was, right? Let's say sine 25 degrees, because this is 25 degrees as well, is equal to opposite over hypotenuse. Where F parallel ends up being equal to 0.007 kilograms times 9.81. That's the force of gravity times sine 25. Let's get that force of gravity, that force parallel. 0.007 times 9.81 times sine 25 gives me 0.02902. All right. It's a pretty small force, but it's a force on a loonie, so of course it's going to be pretty small. We're going to make that negative because it's down the hill. Left side is 0. Take that over to the other side, FSF simply becomes 0.02902, or we're going to round that to 2 digits, 0.029 newtons. Okay? We did it the same way as we've done them all, except that A is 0. Now, there is a shortcut in this question if anybody spotted it, but you don't have to take it. We didn't take it here. Is your hand up for the shortcut? Yeah. Yes. No, that's right. That's the shortcut. If you get F parallel 0.029 newtons, and it's not moving, well, this is how hard I'm pushing, right? I'm not physically pushing it like I was Leah's desk on those days that we were talking about static friction. It's gravity and the normal force pushing it, right? But if gravity and the normal force push it with 0.029 and it's not moving, then the force of friction has to be 0.029, right? So you don't have to go through this process that we did in blue down here if you catch that. If you don't catch that, go through it. It'll still work out for you. It just means a little bit of extra work, that's all. Okay, a little bit more practice on these two guys. Here's your homework for tonight after you've done those problems here. If you haven't finished those problems that you were just working on, by the way, then please finish them up tonight. I'm going to give you a worksheet in just a moment, and I'd like you to do on the worksheet, number 1 and 2. Those are both elevator type problems. I'd like you to do 5, 6, and 7. And I would like you to do, let's say, number 11 and 12. So 1, 2, 5, 6, 7, 11, and 12. Total of 7 questions. Let's get those done for tomorrow. We'll take a peek at them then. All right? That's it for today.